Okay, so we talked about what a basis was in the first video, and now we're going to talk about the coordinates of a vector relative to a given basis. In order to do that, we have this theorem to prove real quick, and it's an important one. If you have a given set of vectors that is a basis for a vector space. Well, first of all, what does that mean again? If we have a basis for a vector space, two things. These vectors are what? Linearly independent. Number two, they span the space, meaning any vector in the vector space V can be written as a linear combination of these vectors. Okay. Now, what this theorem says is one step more. It says if we have a basis, this set S is a basis for the vector space V, then for every vector V, little v, right, in the vector space V, big V, can be expressed in this form. Okay, you say, well, that's nothing new. We knew this, right, because we knew V1, V2 to Vn, they span the space. Since they're a basis, they span the space. So every vector can be written as a linear combination of these. But what the theorem says is it can be written in a linear combination in exactly one way. So that's important, exactly one way. It means for every vector, there's a unique set of these coefficients, k1, k2 to kn, which in a minute we will call the coordinates of the vector. And so in order to do that, though, we need to prove this theorem. So how do we know? We know that every vector can be written as a linear combination, but we did not say it was a unique way, and so we need to prove that. And so let's do that. Let's suppose actually that the vector V can be written in two ways. Let's say, so I'll use the k1 v1 plus k2 v2 plus k n vn. So let's suppose we can do that, and let's suppose that v is also L1. I don't know, use something other than k, L, huh? L1 v1 plus L2 v2 plus plus ln vn. So I say I can write it as a linear combination in two different ways. Okay? All right. So what I'm going to do is sort of play around with this a little bit and see if we can show you that these corresponding coefficients must be the same. Must be the same. So how do I prove that? Well, first of all, I'm going to call this equation 1 up here, and this one equation 2. And what I'm going to do is I'm going to subtract equation 1 minus equation 2. So I'm going to subtract 2 from 1. Okay. Now, on this side, what do I get? On the left-hand side of the equation, what do I get? I get v, what first equation, minus what? V. I think I know what's going to happen there, v minus v. What do I get over here? I get k1 v1 minus l1 v1. So I can combine that as k1 minus l1 v1 plus what? k2 minus l2 v2 plus all the way down to what? Kn minus L and Dn. All right, so I'm subtracting, but I'm combining like terms in a sense. I'm combining using the properties that we have from a vector space to be able to do that, right, for scalar multiplication and so on. So obviously we get on here, we know what we get, right? V minus V is clearly the zero vector. All right. Now here's the neat thing. Take a look at what we have now. I have, remember K1 and L1 are both scalars. So K1 minus L1 is a scalar. This is a scalar. K2 minus V2 is a scalar. Kn minus V, Ln. Sorry, that should be an L. I'm going crazy. That should be an L. K1 minus L1, K2 minus L2, Kn minus Ln. Those are all scalars. So each of these are scalar multiples of vectors v1, v2, all the way to vn. So what do we have here? This is a linear combination of the vectors v1 through vn. And we have them set equal to 0. So what do we know, again, about these vectors v1, v2 through vn? They form a basis for the vector space. And in order to form a basis, what has to be true first? They must be linearly independent. If they're linearly independent, then this linear combination, set equal to 0, can only have what? The trivial solution, meaning the only possible solution is where the coefficients are all equal to 0. All right, so but we say the vectors in the set S, right? We call this set S here. The vectors in the set S are linearly independent. So K1 minus L1 equals 0. K2 minus L2 equals 0. All the way down to what? Kn minus Ln equals 0. Right? So the only solution is where all these coefficients are 0. If there was a non-trivial solution, if like K1 minus L1 was 2 or something, then the vectors would be linearly dependent, which they're not, right? Because they form a basis for the vector space. But if K1 minus L1 equals 0, then what? K1 equals L1. K2 minus L2 equals 0. K2 equals L2. And all the way down here, Kn equals Ln. In other words, what we thought were different values, K1 was something and L1 was something else, we have just shown if we start with that assumption, we've got two different ones, those coefficients have to be the same. Therefore, there is only one unique way to write any vector in the vector space V as a linear combination of the basis vectors. Okay? So that's an important thing. Once we establish that, which we have, we can now talk about these coefficients, right, in this unique, exactly one way, as being what we call the coordinates of the vector. And so let's look at that. So if S is a basis for the vector space V, and so we write a vector V as a linear combination of those vectors, then the scalars K1 through K2 through Kn are unique, and they're called the coordinates of the vector V relative to the basis S. Okay. And then if we take those coordinates, K1 through Kn, and put them in an n-tuple, or which is something that resides in n space, then that vector is called the coordinate vector of V relative to S. And this is the way it's denoted. Coordinate vector of V, we put V, and then in parentheses subscript S. And it's just equal to those coefficients. Now, when we begin to talk about coordinates, it is important that we now begin to talk about what we call an ordered basis, which is one in which the listing of the basis vectors remains fixed. So once you put them in order, right, you can't change them up. Up to that point, up to this point, it really didn't matter, in a sense. In the last video, if you remember, we did this problem here where we said, does this set of vectors form a basis for 3 space? And we said yes, right? We showed they were linearly independent, they span the space. But if I were to take this vector 1, 0, 1 and move it to the end and swap it with 3, 3, 0, that would not change our work down here in terms of the result. It would be the same. We would still have the basis. They haven't changed anything. But when we start talking about the coordinates, then relative, there's a certain order to this. So this K1 has to be the coefficient of the first vector in the ordered basis. K2 is the coefficient of the second one. If I am allowed to change them all up, right, then that totally makes this meaningless. And so it is important that we talk about an ordered basis when we are talking about the coordinates of the vector. Okay, let's look at some examples. If the vector V, which is a vector in 3 space, is 11, 4, 12, let's find its coordinate vector relative to S in each case. This time, first one, easy. S is equal to what? What's this? This is the standard basis, if you remember, for 3 space, what we showed in the last video. You know it as I, J, K, some of you, right? So this is the standard basis. And so you say, well, that's pretty easy, right? Can you write V as a linear combination of these? Yeah. How many of these guys do we need? We need 11, right? 11 of the 1, 0, 0 vector, plus how many of these guys? 4. And how many of this, there's this guy here? 12. Say, well, that's easy, right? So you can do the math, and you see exactly if I do the scalar multiplication and then a vector addition, then I'll get 11, 4, 2. And so, quite simply, the coordinate vector of v relative to s in the correct order, right, are the coefficients, right? 11, 4, and 12. And you say, well, wait a minute. The coordinate vector of v relative to s is exactly the same as the original vector. And that's going to be the case when you're talking about vectors in n space and you're using the standard basis. Okay. However, let's take a look at this. In the last video, and I just showed it to you, we showed that this set of vectors was also a basis for 3 space. This set of vectors is also a basis for 3 space. So now, can we find the coordinates vector relative to s, relative to this basis for the same vector 11, 4, 12? So that means I want to find the coordinates k1 times 1, 0, 1 plus k2 times 0, negative 1, 2 plus k3 times 3, 3, 0. And that is equal to what? The vector v, which is 11, 4, 12. Right. Now I hope by this point that you have gotten the hang of how to set up the system of linear equations necessary to solve k1, k2, and k3 in this case. Right. This will yield the following system, and I'm going to write it in matrix form. Matrix A, the unknowns, and the constants. So this is matrix A, this is X, and this is B. Okay, so right. So if I do K1, 0, K2, plus 3K3 equals 11. How am I getting that? That's the first one, right? K1 plus 0, K2 plus 3K3 equals 11. That's the first equation, and so on. So I get 3 equations, 3 unknowns. So you should be able to solve this system. You can either, in this case, well, you can form the augmented matrix, right? You can take this the constants vector and join it to the coefficient matrix and solve the system. So I'm going to let you do that. I want you to solve this system, and I want you to show that the solution is K1 equals 2, K2 equals 5, and K3 equals 3. You need to be able to do that. Make sure you can set this up. I would make sure I practice this one. Make sure you even, just cover that up, see if you can just solve and get those coefficients, solving the right system of linear equations. So the coordinate vector of v relative to s is, in the correct order, right? K1 first, right? K2 second, K3 third, is 2, 5, 3. Okay? Now, what does this mean? What does this really mean for this vector? It means that the vector v can be written as what? 2 times the vector 1, 0, 1 plus 5 times the vector 0, negative 1, 2 plus 3 times the vector 3, 3, 0. And you should indeed do the math here and make sure that these indeed add up to the vector v, which was 11, 4, 12. Right? 11, 4, 12. I'll let you confirm that. Okay? So the vector, the coordinate vector v relative to s, in this case, tells us take 2 of the first vector, 5 of the second vector, and 3 of the third vector. Add them up, and this is the unique, right, coordinates for this vector. It's the unique location for this vector in a sense. It's where it is in the quote-unquote coordinate system. Now, we can also do coordinates relative to basis for vectors in other types of vector spaces, like matrix spaces. So let's take a look at this one in closing. If M is the 2 by 2 matrix here, 8, negative 2, 1, 9, let's find the coordinate vector of M relative to S in each case. Here we have this is what? Remember, this is the standard basis for M22. Right, these vectors form a basis that are linearly independent and they span the space. Again, this is very easy. You should be able, for part A here, to quickly write M as a linear combination of these four matrices. How many of this matrix do I need? Take a look at what we have here. Clearly 8, right? How many of the second matrix do I need? Well, it's a negative 2 there, so I'll do negative 2, right? How many of the third one do I need? 1. I'm going to put a 1 there. I don't have to, but I'm going to do that just for emphasis so we know what our coordinates are. And then 9 times the last one. Does everyone see what we're doing there? All right, so again, if you scalar multiply each one of these matrices, combine them and add them up, you're going to get M. But this means that the coordinate vector of M relative to S in this case are what in order were the coefficients 8, negative 2, 1, and 9. Right? Take 8 of the first matrix, negative 2 of the second, 1 times the third, 9 times the fourth, add them up. Okay. What about B? What's the coordinate vector of M relative to this basis? So we're not going to show it, but these vectors, which are matrices in this case, 2 by 2 matrices, they're linearly independent and they span all of M22. So we're looking for the coordinates here. So K1 times 1, 0, 0, 1 plus K2 plus K3. So 3 there. Plus K4 equals, put it down here, run out of space. M, if you remember, M is up here, right? 8, negative 2, 1, 9. Okay, so this is takes a little bit of work, but a system of linear equations is developed. And let's go ahead and write these out. What do we get? So the first equation is going to come from equating the entries in the first row, first column, right? So K1 times 1, I get K1, that'll be 0, plus 3K3, so I got K1 plus 3K3 plus 0, right, equals what? That has to equal the first row, first column entry here, which is 8. What about first row, second column? Well, 0, 2K2 plus 0 plus 0 equals what? Negative 2. Well, I think I know what K2 is, right? In fact, we can do this right now before we can go any further. What's K2? K2 clearly has to be equal to negative 1. Okay. Let's go second row, first column. 0, 0, K3, 0. So I get K3 equals what? 1. Well, that's a tough equation. Solved, right? K3 has to be 1. All right. And then what about the second row, second column entry? K1 times 1, 0, 0, K4 plus K4 equals what? 9. Okay. But what else can I do here? I can solve this system pretty easily. I don't need to make an augmented matrix or do anything like that because K3 is equal to 1. Notice here I can replace K3 with 1. I get K1 plus 3 times 1 equals 8. And so K1 is what? 5. And once I know what K1 is, right, 5, I know that 5 plus K4 equals 9. And so K4 is 4. And so the vector coordinate of M relative to this basis is in order, right? K1, which is 5, K2, which is -1, K3, which is 1, and K4, which is 4. So in other words, if I take 5 of this first matrix here, and then -1 of the second one, and then 1 of the third one, and 4 of the fourth one, that's the unique address, right? Can be written, M can be written in one way, exactly one way, as a linear combination of these matrices, and this is it. So that's its vector coordinate relative to this basis. It's unique. Now, I solved this system. This system was pretty sparse. There was a lot of zeros in these matrices, so it was easy to solve. If these matrices all had non-zero entries, you would probably end up with 4 equations and 4 unknowns. You'd want to shoot to the augmented matrix, put it in reduced echelon form, get your solution. You'd have to go do it that way. Okay, so next week we're going to be able to take a look at the idea of dimension. Now that we've talked about a basis and coordinates, this ties directly into what dimension is all about, and so we'll make a definition for that. So you might have an idea already about dimension, and we're going to fine-tune that next week.